But in any case, it is my profound pleasure to introduce Dr. Babar Qureshi, who's currently working as a professor at IBA. He has in the past been associated with LUMS and Habib University. He got his PhD way back from Syracuse University, and I think he was at Trinity College Dublin, if I'm not wrong, for the postdoc.
Dublin Institute for Advanced Studies.
Dublin Institute for Advanced Studies for the postdoc. He has been a good friend of mine over the years, and we've had an occasion to discuss various subjects. He is an excellent presenter, a very good teacher, and a very nice researcher. Today he'll be talking about the quantum structure of space-time and symmetries. Over to you, Babar. Please go ahead.
Okay, thank you very much, Rizwan, for inviting me for this talk. So if I say in one sentence what this talk is about, is I'm going to give this message that the structure of space-time is a crucial input when you quantize, when you do quantization. So when you define a quantum theory, you have to, the structure of space-time goes into how you quantize the theory. And the symmetries of space-time play a very important role in how you do it, at least in how we have been doing this quantization so far. And then the message is that when the quantum gravity is involved, the structure of space-time has a basic conflict with the quantization, and the current research, one aspect of it is to resolve this kind of tension between structure of space-time and quantization. So that's the main message I'm going to give. But since it's a colloquium, I'm going to build very slowly. And in the end, I'll talk about one aspect, one small facet of what we expect from the quantum structure of space-time, which would finally emerge. So let me wait. Yeah, so that's the plan. After a little bit of motivation of why are we interested in this whole subject, I'll quickly move to describing that what kind of structure space-time has, what are our conceptions about it, and then describe how the quantum theory, how it's defined, is affected by the space-time structure, and then I'll argue that why we need a quantum theory of gravity and how it leads to a quantum structure of space-time. Wait, so I have to reduce the size. Yep. Okay. So as we know that we have these three fundamental constants of nature, they are universal in nature, and they define the basic length scales. They define the very small, the very heavy, and the very fast. And it so turned out that when we explored the physics associated with these three fundamental constants of nature, it had always resulted in a revolution in how we do physics. So for example, on this axis, you see special relativity, Newtonian gravity, and quantum mechanics over here. Not only that, but whenever we combined any two physics which has to take into account any two of these, that also led to a new revolution, and that also required a completely new way of doing physics. So like, for example, you have general relativity here, you have quantum field theory here. So the idea is that if I go to this corner where all three of these constants are involved, I need to define how to do physics when they are, all three are important. And it's expected to lead to another unexplored or currently being explored revolution, which is incomplete. So now, what do I mean by structure of space and time? Well, space and time, they seem very simple ideas, but they still have some structure. And it was actually realized very, very long time ago. The Greek philosophers discussed in detail what is the structure of space. So for Aristotle, space was absolute and motion was with respect to this absolute space. and time is absolute and completely separate from space, has nothing to do with it. Then it changed a little bit. Galileo changed it, and he said essentially that all uniform movers are equally good observers. So that means that the space is relative, but time is still outside an external universal clock for everyone. And essentially, what you have is that the space-time stacks, how you thread them together for different observers, only that changes, but the time itself is outside the realm of how different observers see their major different things. This was obviously completely revolutionized with the advent of special relativity, and Einstein told us that neither time nor space is absolute. What is time for one observer could be space for another, and they mesh together to form space-time, and the structure in the space-time is given by the light cones. That means that everyone agrees on the light cones, at least the uniform observers agree on the light cone, and in technical terms, this means that the space-time has a global SO31 symmetry, which is apparent in this form of the metric. This was further very soon generalized by Einstein, and he said that this metric is actually not a fixed thing, it's not a fixed structure. In general, this structure which he had given is not fixed. Rather, it changes from point to point in space, and that leads to the idea of a curved space-time. And one can think of this changing of the metric as if we are dealing with a fabric which is twisted and curved. So as a result, what happens is that the light cones are distorted. Light cones were given by this form, and since this is now distorted, light cones are distorted. But the more important consequence of that is that there are no preferred observers in general, because light cones distort away from any observer. You think of any observer, they are only well-defined straight light cones near it. As you move away, they're always distorted. So there's no symmetry in general in the space-time. And this fact is what we call the reparametrization invariance. There are no preferred observers. Any method of marking the space-time events is as good as any other. This is in fact a gauge symmetry, and it's closely related to dynamical nature of general relativity, because in general relativity, metric itself is a dynamical field which you have to solve for. So a priori, you're not given a space-time. Space-time is an output of the theory. So you don't have any structure imposed on it. And this equation, this is the Einstein's equation, it works in every coordinate system. It takes exactly the same form. However, there is something you are saying about the space-time. What you are saying is that you have essentially you have locally the space-time is flat, and it has, that means that the space-time is essentially a Riemannian manifold. So that's all the structure you have. So space-time is essentially geometry. So the upshot is that the CG revolution was a geometrical revolution. However, one can still have, this is a point which one should stress, have preferred coordinates in a space-time with symmetry. So once you solve for it, you may have a certain solution. That solution may have symmetries, like our flat space-time, which was the focus of Einstein's special relativity, has SO31 symmetry. So a solution can have symmetry, but the spacetimes in general, the theory to start with does not have any symmetry in it. Now, given these various kind of spacetime structure, how do we do quantum theory? Now, quantization requires a reconciliation with spacetime structure, and the first conception of quantum mechanics was actually not even taking care of Einstein's special relativity. It was built up keeping the Galilean structure of spacetime in mind. So, and actually, this is inbuilt in the structure of quantum mechanics. Whatever way we think of quantum mechanics, so far the way we define quantum mechanics is naturally suited to Galilean structure. So what do we have in quantum mechanics? You have a Hilbert space with the representation of canonical algebra of phase space variables, and on this you have a Hamiltonian which generate time translations. So now what do you do with space-time variables? Well, you have the canonical commutation relations. So what you do, you promote the position to an operator. Position is replaced with an operator. And time in this theory is external, because time is the one which defines for you, it acts as a parameter which enters into your Schrödinger equation, or if you want to write your Heisenberg's equations, it enters over there. And as a result, there's no operator for time. So time and space are completely separate. They have fundamentally different roles to play in the theory, which is fine for Galileo. However, this is in direct conflict with Einstein, because Einstein says time is space. So what to do with it? Well, this is usually mentioned in textbooks that you have to sacrifice the position of or the status of position as an operator, and you bring it back to as if it's a parameter. So if it's a parameter, that means it's no longer an observable, because all the observables are in fact promoted to some operators in the theory. So if it's not an observable, so what are the observables? So you have to invent new variables, and these are called the field variables. And you make your phase space using these field variables, and you impose commutation relations on these, and that gives you a quantum theory. So this theory is called a quantum field theory. And I want to stress, because we will come back to this point, that you had to invent new degrees of freedom to deal with, which are completely changed, which have no relation to the previous. They were not part of the theory previously, just to have a theory which is reconciled with Einstein's idea. And this, if you recall, caused a huge amount of confusion in the earlier days when people were trying to write Schrödinger, trying to write the Dirac equation and the Klein-Gordon equation, and were completely confused about it, that what's going on. Well, once you write this theory, then even then, to describe the nature, you have a huge amount of technical difficulties, and people are obviously still studying this theory. But the point is that even to start with, you had to make a big leap, a big new idea of how to do physics. Well, you can demote the position operator to a parameter. There's still a lot of work to be done, because as I told you, that this is how the quantum mechanics is done. So you still have to pick a spatial slice to quantize, and time is still an external parameter. So what happens to the fact that there are different Lorentz observers for which time slicing and spatial slicing is different? So what you really do is for different time slicing or different choice of these spatial slices, you have different quantization. You essentially have different quantization and quantum theories for each choice of spatial slicing, or for each Lorentz observer. So then how do you reconcile with Einstein's idea that you have this structure, a symmetry of spacetime? Well, you restore it by demanding that the fields are representations of the Poincare group. So essentially, these different theories, which one should think of different theories, are related to each other, and you can map the results of one theory to another, and that gives you a representation of Lorentz of the Poincare group. So essentially, the Lorentz invariance is restored. Otherwise, it's still the old quantum mechanics. You still have a Schrödinger equation with an external parameter, which takes exactly the same form as if you were doing the Galilean quantum mechanics. So not only you have to choose these Lorentz representation on fields, which by the way is responsible. It's kind of a prediction of the theory because of this demand that you have various spin particles. But you also have to impose microlocality, that these fields commute outside these space-like kind of separations, and this is crucial for this. This will again come into play later on. Now, what this was, this was the story of reconciliation of uh, special relativity with quantum mechanics. Now, let's go to the one step further and consider. Can you give me like 1 minute because there are azans going on here? So I'll wait for the azan to finish.
Yes, go ahead. Go ahead. So right now we're just waiting for Babar to get done with the background disturbance that he was experiencing. So just please hang on. While we're waiting for Babar to come back to the meeting, there are a couple of questions that have been posed. So why don't we all just read those questions, and when Babar comes back, we can ask him
Yeah,
if he
I'm
wants to
back.
take those. Okay, excellent. So Babar, there's a couple of, I didn't want to interrupt the flow, but since the flow has already been interrupted, there are a couple of questions that students have asked. Maybe you want to take them now or maybe later, that's up to you.
Well, if you could, maybe let's, if you could read and pose them
Sure,
here,
sure,
because
sure,
as
sure.
you,
Yes, the questions are in the chat box. They're already there in the chat box. I can read them out. So the first question is just a simple question. What is a gauge theory? So
yeah, I mean, this is a very general question. Let's wait for it till the at the end.
I see. The other question is maybe not entirely relevant. Isn't a bigger problem between standard quantum mechanics and relativity the freedom of frames? As in, how does Schrodinger's cat see its fate in its own frame? Will these questions be passed up to by this reconciliation?
Well, I don't know. I mean, how does the Schrödinger cat sees its fate in its own frame? I don't see the relevance of it to what I'm saying.
Okay, very good. Roughly, so questions dealt with, and now you can proceed. Thank you.
Sorry about that. So, so now, so we have like seen like we encountered a trouble when we encountered a new structure of space-time, and Einstein created us a problem of the next level and dispensed away the structure which he first gave us and gave us a more general structure. So let's see what happens in that case when we turn on the G, that means when the gravity is present, how to quantize them. Well, at the first level, we just deal with fixed geometric structure. Remember, in the complete theory, even the geometric structure is a dynamical variable. But even if we don't assume that and we consider a quantum theory on curved spacetime, how to do that? So, for example, again, taking the idea from the previous notion that we start with some kind of a field theory and try to quantize it. Maybe that will help. But in this case now, this G is no longer the Minkowski metric. It's in some general spacetime metric, which would in general will not have a symmetry. So that means you do not have the Poincare invariance, the structure of the Lorentz group, which was present in the previous case, which helped us in quantization, is no longer present. So observables become very hard to define. And what happens is that, as I said, that always you always need to pick an external time to quantize. And choice of time is equivalent to choice of slicing or choice of a choice of space-like hypersurfaces in your space-time, which threads to your time variable, and that is a choice which you have to make. In the case of Lorentz invariant theories, we had some special slices available, which were the ones which gave us the nice light cones, and choosing one of them was equivalent to choosing any other of those because of having a Poincare representation available for the whole spacetime. Now, when you do not have that, then it becomes completely free that how do you choose a space-time slice to quantize. So quantization requires choice of space-like surfaces, and different choices actually give inequivalent answers. It's not just that the physics looks different. The answers, as far as we can tell, they look really inequivalent. At least we do not understand how to quantize in a manner so that we can map the answers from one setting to the other. There are some partial answers how to deal with such situation. Well, obviously, if you have some symmetry, like you have stationary spacetimes, then you can have a special time direction which you can choose. Or there are some technical requirements which have been proposed, like this Hadamard condition of how to choose a quantization. However, no matter which time slicing you choose, you still have the local Poincare symmetry is still part of your spacetime. So various spin representations are still present and is a direct consequence that you have a local Poincare symmetry. But you have run into a big problem because you do not know which time to choose. Now, but one can write these theory and choose some time slicing and try to see that what happens. So even in those cases where you have some control over how to define the time slicing, like having some stationary aspect to the space-time, the results which come out from this theory are very mind-boggling. So what you do, you push through this theory and try to compute a few things. So for example, what you can do, you can ask that if I probe some physics at very small length scales, let's say this length scale is L. So our traditional thinking about this is that you have to use some kind of a light beam or some kind of probe with wavelength which is comparable or smaller to this length scale. But that wave will bring with it a certain amount of energy, which you can think of as mass as well. And what you are doing, you are concentrating that energy into dimensions of size L, because you're probing this size L. And that leads to formation of black holes, because a black hole has a Schwarzschild radius of this size, 2gm over c square. And if you take this mass and plug it in here, what you find is that when the length which you are probing reaches, this should be, by the way, L square. So when the length reaches, no, not L square, it's just L. When the length reaches the size of the Planck scale, then you have a Schwarzschild radius being formed, a black hole being formed. And as you go deeper, as you try to go deeper, so your intuition is that you will choose even smaller lengths that will only going to increase the Schwarzschild radius. So the connection, which is usually taught in textbooks, that to probe smaller lengths you need higher wavelengths or higher energies, is completely inverted. So UV becomes IR, and you have a complete destruction of manifold structure, because these tiny black holes completely distort of any smooth structure of space-time, and we cannot think of space-time as smooth. So this is sometimes called a quantum foam. So what you have fundamental limitations on how deep you can probe, and there's no clear concept of length smaller than Planck length. This is the phenomena which appears in many different forms, in many different approaches to physics. Like it appears as T-duality in string theory. It appears in other approaches to quantum gravity. For example, you have minimum areas and volumes arise in loop quantizations, strings, and almost all other considerations of quantum gravity. You always run into this problem. So you have severe distortions of the space-time structure at Planck scale. So that means you have pushed to a limit where the structure of quantum mechanics and the space-time structure, which Einstein told that is a manifold, it's a Riemannian manifold, they're not compatible, and pushing one leads to destruction of the other. Well, actually, the merging together is so bad that not only the manifold structure seems to be destroyed, but even the quantum mechanics itself doesn't make any sense. So for example, Hawking did this thought experiment. Thought experiment is just a calculation. So he found that the black holes, they radiate through thermal radiation. And one easy way to think of it, think that time is going upwards and the horizontal direction is the spatial direction, is that and this is the Schwarzschild radius. These pink, these orange lines are the Schwarzschild radius, and there's singularity, pink singularity in the middle. So if you create a particle-antiparticle pair, which are always created and destroyed in the quantum vacuum, but when this happens near a black hole, then one of the particle can fall into the black hole and the other just goes out, can go out to the infinity. So the black hole has essentially polarized the vacuum and created the particle. So this particle flux, what Hawking found, has a thermal spectrum, and as a result, the black hole acts as a hot object with entropy given by this. Now this leads to many paradoxes. First of all, one could ask, where does this entropy comes from? Because all you have is one solution of Einstein's equation, so how come empty space has entropy? But a bigger problem is that it leads to information loss. So suppose this star is collapsing and forming a black hole. So once the black hole is formed, it starts radiating. And as it becomes smaller, it radiates even at higher and higher rates. So finally, the black hole has to go away, and you are left with all the mass which was in the star is radiated away in terms of thermal radiation. Now, if you throw in anything inside the black hole, it's going to come out as thermal radiation. So all the information is destroyed except for the global charges. You just know what was the mass and charge of the things you threw in and nothing else. So this may look fine, but this is not fine with quantum mechanics at all, because it's essentially saying that you can turn pure states into mixed states, while quantum mechanics does not allow it. And this is so sacred in quantum mechanics because this goes against the unitarity of quantum mechanics. And if you don't have unitarity in quantum mechanics, you do not have even a sensible interpretation of probabilities. So this is completely fundamental to quantum mechanics. So in essence, what this tells you is that the quantum mechanics itself does not make any sense once you combine it with general relativity. So we have a need for quantum theory of gravity. Let me leave this part. So how would you quantize the gravity? Well, again, let's just go back to the simple idea of, let's just choose some hypersurfaces, and we have some variables. The variables in this case are the metric of the space-time, and just see if we take this phase space and quantize using the usual rules of quantum mechanics, what happens. So fortunately, so again, as I said, that always when you quantize, we are stuck with Galilean idea that we have to choose a particular time. We have no other way of doing quantum mechanics. So you have to decompose your as yet unspecified metric, unspecified space into the hypersurfaces, which is actually can be done, and the unknown metric degrees of freedom, a general metric, can be decomposed like this, given by using the ADM's decomposition, and you find that you have a phase space action, where this Qij is the spatial metric on this surface, phi is just some matter fields, and you have these phase space variables. So if you look at this action, you find that it has a very interesting structure. This H is the Hamiltonian, but this is coming with n, and n does not have a corresponding conjugate momentum. So this H and similarly the Ci, they become simply constraints. So Hamiltonian is a constraint, H is 0, and similarly there are diffeomorphism constraints to make the theory background independent. And this was completely expected, because the time has no reality. Time is just a marking in Einstein's theory. So any time choice and any spatial embedding is totally fine, and that gauge freedom is contained, is manifested in these two equations. So this becomes like something like a gauge theory, and Dirac told us how to quantize these kind of gauge theories. So he just said that impose these gauge constraints on your wave functions, and that's what you can do. And you get this kind of equation. So this equation is what you call the Wheeler-DeWitt equation. H psi is equal to 0. But this has a problem, because it says that Hamiltonian is 0. So you are in a stationary state. And in this stationary state, you never come out of it, because this contains everything in the world. And you do not have any evolution in your theory. So you do not have any time in your theory. So this is called the problem of time. So one idea to solve this problem of time is that you have to choose some internal degree of freedom, some matter degree of freedom as a marker of time. But an internal degree of freedom, a matter of degree of freedom, will be composed of some kind of matter, some quantum field, which will be subject to quantum fluctuations, and time would then become an operator. Then this has many technical problems. Finding an inner product is very, very hard and impossible to impose microlocality, causality. No one can impose it, and that probably one has to live with it. Same kind of, not same, but other problems exist if you quantize the theory perturbatively. For example, the perturbative approach tells you that there should be gravitons, but it has many problems. So for example, if you just quantize simple metric fields, you find that the theory does not make much sense, although some people are now working on it to finally, maybe they have the idea that maybe finally this theory is making sense in the ultraviolet, but that's an ongoing program. Another approach, which is again a perturbative approach, is of string theory. It does give sensible answers, but it has its own problem. So, for example, it's background dependent and it has a huge landscape problem. And what you have here is that you have emergence of new variables to quantize, strings, banes, and so on. So, geometry just becomes physics. So what you have is new variables, as we had encountered in going from Galilean structure to Lorentzian structure. We had to invent new variables. It seems like you need new variables here. Similarly, when you are using this canonical quantization of gravity, again, what you find is that you are in need of new ideas, because you don't even know how to define evolution in this theory. So the lesson is that the quantum mechanics is in need of new structure to quantize, and current quantization of GR degrees of freedom is troublesome. And as I showed you through a thought experiment, that space-time structure is itself in doubt, so maybe we need new paradigm. Perhaps we don't yet know the appropriate variables to quantize, and that has led to many people to speculate about emergent spacetimes. And there are many ideas about it. It appears, for example, in M theory, ADS-CFT is considered to be one manifestation of it. And causal dynamical triangulation, it starts with discrete structures and finally gives you a smooth manifold structure. So almost all ideas of quantum gravity lead to a space-time which is no longer a manifold. So one aspect of this quantum structure of spacetime, which is not yet understood that what form it would finally take, is that it will have some kind of non-commutativity. So field theory probes of spacetime and Planck scale imply uncertainty relations among coordinates of this kind. Like if you measure two coordinates, they will not commute. And even you have these relations with position and time as well. So these can be modeled by a quantum spacetime. So instead of just having this kind of uncertainty, this commutation relation between position and momentum, you can have the same kind of commutation relation between various spacetime coordinates. So how to do physics on these? So fortunately, there's this algebraic approach to doing physics started with von Neumann and then developed by Haag and others, and Gelfand, Naimark, and Siegel gave this very profound theorem which have far-reaching consequences in physics and in mathematics and topology in general, is that the algebra of functions, the original motivation was about the algebra of observables. So in this approach, everything is about the algebra of observables. So what you think is that the space-time is composed of functions. You can think of it as functions living on this space-time. And the algebra of functions, the Gelfand-Naimark theorem shows, contains in it all the topological information about the space. Then cones, and then Gelfand and Naimark actually show you that when this algebra is considered to be the algebra of observables, how to reconstruct the Hilbert space from there. But Combs extended this theorem, and he said that if you have a suitable differential operator on top on this algebra of functions, then you can even recover the geometry. So all the geometry of a space-time can be recovered from the algebra of functions along with a differential operator on it. Then Cones extended this idea. By the way, Cones won Fields Medal for this work. He replaced the algebra of functions by, he said, well, if we have got an algebra, so who stops us from making this algebra non-commutative, considering a non-commutative algebra, and then repeating this game. So what you have finally is a well-developed theory of non-commutative spaces, but Cohn's work is mostly on the mathematics side, how to define a non-commutative space-time. It turns out that this non-commutative kind of space-time actually emerges from many approaches, like matrix models of M theory. They give emergence of space-time, which is typically non-commutative in the intermediate steps. So finally, in the infrared, you're going to recover the smooth manifold, but in the intermediate steps, first you see a non-commutative space-time emerging. And it, as I said, even the field theory probes hint at this. But that's just the mathematical structure of the non-commutative space-time, how to do physics on it. So in this case, you can use this idea of Moyal, who described quantum mechanics using NOT operators. He said, I'm going to just do it using the phase space, functions on phase space. And what you do is you encode the algebra, the Heisenberg algebra of x and p not commuting, into a kind of a new product on these functions called the star product. And this star product, which is written over here, Moyal product, it actually gives you the kind of algebra you want, this one. This is tailored to give you this algebra on the ordinary functions. So once you have encoded this algebra on ordinary functions, then you can, the idea is to just write the actions, field theory actions, and replace the products by these star products, and that's gonna give you the physics on non-commutative spacetime. However, there are some problems with this approach. So first of all, you have explicit breaking of Lorentz invariance over here, because this algebra is not Lorentz invariant. So that means you're writing this action, and this action is supposed to be of some fundamental theory at very fundamental scales. But there's almost no justification of even writing this action, because these actions in the first place were written because of having Lorentz invariance in mind. But now you don't have Lorentz invariance at the fundamental level. So why one is writing this action? There's no justification. So the question is, what is the symmetry principle replacing local Lorentz invariance, which leads to these kind of actions? And if there's no, this is actually a question of much more fundamental importance, the second one, which is probably even unrelated to this non-commutative structure of space-time. And the question is, if there's no Lorentz invariance, where do spins come from? Because spins are representations of Lorentz symmetry, which is present even in case of general relativity at the local scale. So where do these spins come from? And also, recently there have been these gamma ray burst results, where people observed some photons traveling to billions of light years, and they are expected, if they encounter these photons, encounter this non-commutative structure of space-time, so this should leave some imprint on the photons if there's a breaking of Lorentz invariance, and that should lead to some kind of change in dispersion relations of the light of these photons. But they haven't found anything, and the limits they put, they go deeper than the Planck scale. So that is kind of a strange result, that how come we don't see the imprint of this distortion of space-time at deep Planck scales imprinted on these photons. Well, with these in mind, there is this idea of giving a quantum symmetry principle for these quantum spaces. So the idea is that you want to recover your usual physics at some scale, but then you have to start with some similar looking action. And where does a symmetry principle come from for that? So that's where this idea of quantum symmetry comes. And what you have is you have a quantum group which generalizes the usual group which describe the usual symmetries. And a quantum group G is essentially is described by a product or a group product and a coproduct, which is different from the usual coproducts. So, but I suppose most of the people don't know what a coproduct is. So, what is a coproduct? Coproduct is essentially a map from group to the tensor product of groups. And actually, one should not think of it as group only, but the group algebra. But group algebras are very natural in quantum theory because the groups act in quantum theory only through representations in Hilbert space. So whenever you have a representation of a group, you automatically have a representation of a group algebra. So essentially, the quantum Hilbert space doesn't know about group; it only knows about the group algebras. And then you have to have a representation uh, of a tensor part of group algebras because you have multi-particle states in your theory, and this coproduct essentially defines how do you act in a tensor part of representations. How do you form the tensor part of representations? So whenever you make a tensor product of representation, you are assuming a kind of a coproduct. But in usual cases, it's just taken to be this simple coproduct, which I have written over here, which gives you the normal kind of symmetries. And essentially the normal Clebsch-Gordon coefficients, which you are familiar with. But this coproduct can be given the meaning of defining the action of a group into spacetime algebra and defining an automorphism. So what you have, this M, F and H are functions on the spacetime. M is some kind of a star product, any product. It could be the simple pointwise product or the star product or any other funny product. So how the group X in the spacetime, it has to respect this kind of structure because you have to give an action that how this group acts, and you're going to say that this group is an automorphism if this holds, that the action is defined through action of the coproduct which is compatible with this multiplication. Now the usual coproduct over here is not compatible with the star product algebra. So you have to invent some new coproduct, and what you realize is that there is still a symmetry. It's just that you have to change the coproduct. However, even the new coproduct is a homomorphism of the group. So it really is a symmetry. It's just that it's a different kind of symmetry. And one of the consequences of this is that since the coproduct defines the action of symmetry in tensor product of representations, the R matrix of the quantum group controls the statistics of the field. Here, this R matrix is essentially an intertwiner, which tells you that if you have a coproduct, think of it as a representation of, let's say, two particle states. Then when you act with this R, it intertwines and gives you the opposite order. Tau is flipping the order in the tensor product. So it flips the order. So what it's essentially telling you is that since R is non-trivial for this coproduct, is that when you exchange two particles, you do not get a fermion and boson, you get something more funny. So one can use this quantum group to give a symmetry principle for quantum field theories on non-commutative space-time, and one can actually construct a QFT. One finds when one goes through the steps that indeed the statistics of the particles is deformed. Like for example, you can get something like this. And the symmetry demands that if you write an interaction using a field the interaction has to be written using a star product. So what you have is that the non-commutativity of the space-time emerges as a consequence of symmetry. So you have restored the role of symmetry to a huge extent, and actually you have discovered more. What you have discovered is that the algebraic structure of the space-time is tightly knitted to the what kind of symmetry you want to have over there. So you have something like this. Half symmetry, when I say half symmetry, I mean that to define the symmetry, you not only have to give the group structure, but also its coproduct structure. So once you fix it, your space-time algebra is fixed. And space-time algebra includes, if you want to have usual algebra of manifolds, or you want to have something more non-trivial like a non-commutative space-time. And similarly, your statistics is fixed. And these arrows can go in any other direction. If you fix the space-time algebra first, you're forced to pick a particular half symmetry, and you're forced to then pick a particular statistics. Similarly, you can start from here and go in the other directions. What then you have, you can compute different things. So one result is that dispersion relations of particles are not changed, so you are safe from gamma ray burst result, and this kind of explains that why the gamma ray burst did not see uh, the quantum form structure of the space-time. And what you find, for example, even the free theory has very complicated Weidmann functions, which you expected because you knew that your theory, like if I come back over here, that it's impossible to impose microlocality and causality. This is expected of all quantum gravity theories, and since this non-commutative space-time is capturing an aspect of quantum gravity, you find that the Weidmann functions of the theory are non-trivial, and you get a non-local and non-Gaussian theory even in the free case, which was expected from quantum gravity effects. So much more work has been done, including formulation of gauge theories and gravity, and also a lot of work needs to be done. So thanks for listening.
Thank you very much, Babar. We can now open the floor for questions. I see some students are putting in questions. Okay, Manur, instead of typing it out, why don't you just unmute yourself and ask the question?
Sir, am I audible?
You are audible. Please go ahead.
First of all, thank you for your session. It was very insightful. The first question I've asked is that what does it mean for a theory to be background independent, and what physical significance would that have on resolving some of the technical difficulties you've outlined regarding different theories? And the second question is about the statement that you mentioned about that non-commutativity emerges as a consequence of symmetry. So is this something that is it a desirable result, or is it further causing problems for us in other theories?
Well, for the second part, I would say, I mean, this doesn't cause any problem. I would say it's desirable, but I'm not sure, like, uh, how much of it would be part of the final theory, how much of it will be retained, because you have to remember that all these attempts, no matter how people sell, are just the attempts so far. We do not have the perfect, or probably not even the correct idea of how to deal with quantum gravity. So that's what I would say about the second question. The first is about the background independence. So the idea is that some people feel that when Einstein discovered general relativity, and it has been an overall theme in physics, that when you discover some revolutionary physics, you do not discard it away. You do not then completely throw it. Newton is not irrelevant now. So what Einstein has discovered in the form of general relativity, where the space-time is considered a kind of a manifold. So it's a geometrical object. That means it does not depend on the coordinates you put in, and the geometry comes out as an equation. So Einstein's equations are part of our current understanding of the nature. Now, in many of the theories of quantum gravity, like for example string theory, what you do not solve anything like Einstein's equation directly. You assume a solution of Einstein's equation and you quantize on top of it. So some people feel that this is not really quantizing the theory itself, because quantization traditionally means something else. And it's also essentially just doing away with all of Einstein's main lessons, that the space-time is a solution of something. So that is the issue with background independence. And obviously, people claim that if you had background independence, then many of the problems will not occur. So, for example, as I said, that we do not know how to quantize in any given background. If you take a background and it doesn't have Lorentz invariance, it's not very clear that how to quantize even a field theory and how to give meaning to it. People are working on it, and it becomes very technical, and the results are few and still not like coherent. Not many people try these kinds of things. People who are very meticulous about what they're doing, only those people are trying on those lines. Like one of the main proponent I would say is Bob Wald, whose general relativity book you might have seen. uh, so the idea so again so the idea is so that if we knew how to do the theory in a background independent way, maybe a quantum field theory, it will emerge from it how to do quantum field theory on a curved background, because the background will emerge along with the quantum theory as a solution of the equation.
Okay, very good. Thank you, Babar. Hassan, can you go ahead and ask your question?
Yes, so like I have a general question, like just say when we consider quantum field theory in the like path integral formalism, so what we essentially are doing is like a path integral we take over the field, right? Like when we want
Path
to
integral
move on
will
to जो हम path integral लेते हैं,
हम्म
that is like essentially over that is like वो d phi होता है उसके अंदर,
जी जी
the
जी
in your action you have like the field phi, and उसके ऊपर basically you're taking the path integral. So when you want to quantize gravity, when you're at the action s on like a curved space time, तो उसके अंदर metric होता है g. Why can't you just like do the same thing for g, like write a path integral over g as well?
Well, you can do that, but the point is that when you do path integral, it doesn't. It's supposed to be equivalent to this canonical quantization. So it's not going to remove any of these problems. Actually, it has its own problem, because the path integral is not essentially defined for anything, even for the normal quantum field theories. It just gives you a handle on manipulating some calculations more intuitively, you can say that. So when you can define the path integral, but it leads to the same problems.
Okay, and I have another question. Like at the end of your talk, you referred to the fact that like the theories जो जिस तरह से हम construct कर रहे हैं, they end up being non-local. I mean, doesn't that violate special relativity?
Well, yeah, that's the point, that special relativity is expected to fail at small distance scales.
Yeah. Thank you.
Okay, I see Mohammed also has his hand raised. Please go ahead and ask a question, Mohammed.
Am I audible?
We can hear you, yes.
Oh, okay. So my question is that, like Dr. Babar mentioned, space-time slicing in the lecture. So I wanted to ask that how is space-time slicing possible when the space and time are constantly getting intermixed with each other? And secondly, if you also mentioned that different slices produces different results, so can't we calculate which is the best way to slice the space-time, and different, and if same degrees of internal freedom could be used for different slices? And my second question is that Dr. Babar mentioned a equation in which there is the Hamiltonian acting on a state function and giving zero. I think it is the Wheeler-DeWitt equation. So how does the Hamiltonian destroys a state function, and what is the state function referring to in that equation?
Well, let me start with the last question because I kind of keep forgetting the first one. So in the last one, it's acting on the state function. The state function is supposed to be the wave function on the configurations of the metric. So essentially, it's a probability distribution amplitude on what kind of space-time you will have. So because your degree of freedom is the metric, is the space-time itself. So it's a wave function of that. And you can call it the wave function of the universe or wave function of the space-time. And Hamiltonian destroying it is not something very peculiar. It's just, suppose if you were in ground state, then your ground state is destroyed by the Hamiltonian. So it's like that. So it's saying that any acceptable wave function is just like in the ground state. So that's why you say that there's no dynamics. There's only ground state. It's like everything is, you have different states, but they are all in the ground, like of the ground state. And the first question was,
Could you repeat the question? Could you repeat the question?
Okay, so the question was that how is space-time slicing possible when the space and time are constantly getting intermixed with each other? And is there a method to
well,
calculate
space and
the
time are not getting, you have to define, you have to explain what you mean by they're getting intermixed. They're getting intermixed precisely because different slicings are possible. So for you, you have never confused a meter stick with a clock. I'm sure you have never. So it's just the issue is that different observers, they between different events, what you call that there's a meter stick, only a meter stick is enough to measure the distance between them. Some other observers will say no, you need a clock as well. So space and time get intermixed precisely because different slicings are possible. But the problem with quantum mechanics is that you have to choose a slicing to quantize.
So like can we calculate the best way to slice the space-time?
Yeah, if we could, the problem would be solved.
Yes, I mean that's the
But
whole.
then you would still have to explain like what happened to Einstein's theory, which allows for different slicings.
Okay, do see Hassan's hand raised again. This is probably going to be the last question that we'll take. Please ask your question, Hassan.
So I have a follow-up question on your answer to my previous question. If, as you say, special relativity is supposed to fail at microscopic scales, and that causes the emergence of non-locality in your like quantum gravity. So what do we replace special relativity with?
Well, what do we replace it with? I was giving one proposal in the talk, but I mean, the idea is like.
if somebody knew, then perhaps this talk might have been
Yeah.
obsolete. So or it could have been, hey, we know exactly what to do.
Yeah.
Okay. Thank you.
Right. So I guess, I mean, that was from what I gathered, one of the main points was that, I mean, there are many proposals and we're still trying to figure out what's going on. Baba, would you like to make any concluding remarks? And that would give somebody a chance if they might want to ask a question. We can perhaps retain Baba for another few minutes. Is there anybody who might want to ask a question? And if not, it's over to you if you want to make any concluding remarks, and then we're done for the day. Thank you very much.
Well, I'll just say thank you for inviting. And I suppose these are students at LUMS who were asking questions.
Actually, I'm not so sure. A few
Okay.
of them probably are. I know Vahaj for certain is. Hassan may or may not be. They can answer for themselves. But yes, we do have. Oh yeah, Hassan says he also is a student at LUMS. We do have people joining in who aren't LUMS students, but we do have. I do recognize quite a few of these names as being LUMS students. So the people
Yeah, I
asking
mean,
questions.
like it was nice talking to the students, and as expected, they were like very intelligent and thoughtful questions. So it was nice.
It's always a pleasure to have you, Babar, and we hope that we can, at some point, go back to our previous arrangements of actually seeing the speaker in the room. As it stands, we're still sticking to a Zooming format for the most part, but it was very good to, like always, to have you over, albeit virtually this time. So thank you. Have a good day. And
Thank
thank
you.
you
Bye
everyone
bye.
for listening. Thank you everyone for listening. Okay, bye-bye. Stay tuned for the series. We will have weekly talks. The normal time for our talks is 3 p.m. on Thursdays, but some of these talks, sorry, 2:30 p.m. on Thursdays, but sometimes the talks would be arranged at 6 p.m. Because of availability issues with the speaker. All right. Have a good day, everyone. Bye-bye.